You'd have to breathe this uranium in or swallow it for it to cause you cancer.
So you keep it in a secret vault to protect people from eating the uranium. They're going to be looking at smarter every day. Specifically, if you watch this video, you will understand nuclear power. Let's see how accurate it is. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's see.
A third of the electricity in my house comes from nuclear power. That's how this sign is lighting up. There's a nuclear power plant.
It's actually more than my house. I'm not sure where he lives.
Down the road, it's making the electricity flow through this gas, and it's lighting things up. You know,
that would put him somewhere in the southeastern U.S. Places like Georgia or Alabama get about a third from nuclear.
What else is powering? These lights right here. Today on Smarter Every Day, we're going to start something that I've been wanting to do for oh so very long. I just haven't done it because I've been a little nervous because I want to get it right. We're going to start the Smarter Every Day deep dive series into nuclear power.
Cool.
I want to get this deep dive series right because when people hear the term nuclear, it's a loaded term. I mean, most people come to their awareness of the raw physical power of atomic energy through knowledge of atomic weaponry. We've rightfully been taught for years to...
I've also heard a lot of people, the first time they've heard the term nuclear was in the context of waste, and don't even necessarily correlate it with power plants, necessarily just waste from, manufacturing or any other byproduct, and usually involves green goo and infamous yellow barrels.
Fear these weapons.
What are you supposed to do when you see the flash? Duck and cover. Tony knows the bomb can explode any time of the year, day or night. He is ready for it. Duck and cover. Atta boy, Tony.
Yes, this wall will surely protect me.
That flash means act fast.
So in order to do this right, I want to move from knowledge to understanding about how such an incredibly powerful thing can be harnessed safely for the good of humanity.
It's not just power, it's something that a lot of people just don't understand. If people were approaching it logically, they would be afraid of the sun. They would be afraid of solar power because the sun can cause burns and skin cancer, which makes about as much sense as people being afraid of nuclear.
So I think an appropriate place to start is the first place.
Which is funny because the sun's a fusion reactor and sunburn is a form of radiation burn.
That ever happened. EBR-I, the world's first nuclear power plant. How did it work? We're going to figure that out today. And
that one was a weird one.
Gain an understanding of nuclear power. That's what I want to do with this deep dive series. We're going to see people handling nuclear waste. We're going to meet this long-haired guy that's glass blowing to measure temperatures inside nuclear reactors. We're going to meet people that make this stuff happen, and they're interesting, and they're smart, and they're compelling, and I'm excited. So,
even everyone I've met working within the nuclear industry has generally been passionate about what they do. There's a lot of different jobs, from technicians to operators to engineers to people that work in the medical field to operations managers to people that have nuclear experience and are using them in other industries such as in oil and gas. But there always seems to be a certain spark and passion, I've noticed, because it's a very specialized field. You kind of have to be a little out there and interested in weird things in order to get really into it, because every position in nuclear seems to take a lot more education and experience requirement than that same position in a different field. Like, take a plant operator, for instance. Plant operator at, say, chemical plant or an oil refinery or something like that can get qualified in a matter of weeks. But a full journeyman plant operator at a nuclear power plant, it can take the better part of a year, if not a couple of years, depending on how they schedule, the classes and getting qualified each individual watch station and doing all the different all the different operations and maintenance that can only be scheduled certain times a year. So it's definitely quirky and extremely nerdy, which is why it's amazing.
Here we go. This is the first video of many of the nuclear power deep dive series here on Smarter Every Day. So make sure you're subscribed, maybe even sign up for the email list because these videos are incredible. I don't know if you know this, but there are 17 Department of Energy national labs all throughout the country here in America. And these places do all kinds of incredible research that's going to help us have a new clean power future. And I'm really excited about that. To get started, let's go to a very interesting place.
If you want to learn about nuclear reactors, the best place to do it is out here in the middle of Idaho at a place called Idaho National Laboratory. Let's go get smarter every day and learn about nuclear power.
So about an hour outside of Idaho Falls, Idaho, there's a building that was made in the 50s. This is the home of EBR-I, Experimental Breeder Reactor 1.
So I've never actually been there, but it's fun because they turned an old reactor into basically a tourist attraction, which is nice.
And I went inside and met Andrew, who's going to show us all about how EBR-I worked.
Okay, here we are at EBR-I, and this is Andrew.
Hello, folks.
You're going to walk us around, right?
Yeah, I suppose so. I'm not sure. Did you have any specific questions for me? Do you want to just...
Okay, I could tell at a glance he's the right kind of crazy nuclear guy. Yeah, he's going to be a good guy.
Look around and take a look at everything.
Yes, I do. EBR. What does the EBR stand for?
So that's Experimental Breeder Reactor 1. We had breeder piles before this, but they weren't technically reactors. This is the first real breeder reactor.
What is a breeder reactor? What does that mean?
Ultimately, a breeder reactor is taking uranium-238, bombarding it with fast neutrons to produce plutonium-239.
Okay, don't freak out. I know.
In the context of this specific reactor, yes. There are other reactions that could do something similar. So the thorium reactors, for instance, thorium-232 absorbs a neutron, then undergoes a couple of beta decays and becomes uranium-233, which is the active fissile ingredient. But uranium to plutonium is the most common one, and it can happen in non-breeder reactors as well. But for it to be considered a breeder reactor, you need to make more than what you consume. At the nuclear power plant I worked at, uranium-238 was still bombarded with fast neutrons and turned into plutonium-239, but fast neutrons only consisted of a small portion of the reaction, and it wasn't enough to sustain a cycle. It's enough to extend a fuel cycle, but not to sustain it by itself.
That was a lot of words, but we are totally going to understand what he just said.
The reactor is taking uranium-238, bombarding it with fast neutrons to produce plutonium-239.
Okay, don't freak out. I know that was a lot of words, but we are totally going to understand what he just said.
Okay, let's see him break it down.
It's best to start upstairs.
Let's do it. I'm following you. This is awesome, by the way.
I mean, this place was built in 2 years, which is truly incredible.
I like that it looks like an old school fire station now or something.
I always joke with people who come through that I'm not sure that we could build a shed in 2 years nowadays, let alone a whole reactor.
Oh, by the way, I just went to the restroom a minute ago, and it just looks cool because you can, I'm sorry, I'm going to do this.
Hopefully no one's in there.
You can see all of Idaho wilderness out there. It looks awesome.
Good spot to do something experimental.
It's just a cool place. So the fonts are great. Love it.
I think we'll probably start in here just to get a bit of a rundown of things.
All right.
So this diagram helps me explain breeding just a little bit. There are two isotopes of uranium that occur naturally, 235 and 238. Uranium-235 is what's useful to us in a reactor. That's an unstable atom.
235 occurs naturally, but it only has a half-life of about 250 million years. And considering the Earth is well over 4 billion years, a lot of the natural 238 has decayed away. A lot of the natural 235 has decayed away. Compare that to 238 that has a half-life of 5 billion years, so a lot of it's still here.
We can break it apart and harness the energy from that breaking. Unfortunately, 99.3% of uranium is 238, which is too stable to be split, but you can use it to make plutonium. So what you have to do is separate the 235 from the 238 until you've got a concentrated amount, and then you can build a breeder reactor.
A breeder reactor typically requires much more enrichment, upwards of 15% compared to the 2 to 5% for a typical commercial nuclear reactor. And that's because it needs to breed it needs more fast neutrons, which you're just not going to get with the lower enrichment. Which is kind of paradoxical, because in breeding you want to use more plutonium than uranium, but you need all this uranium in order to get the plutonium.
Now, so you're breeding plutonium, so you're making plutonium, and that's what's actually giving you ultimately the electricity?
Not in this case. So the uranium-235 is kind of running double duty. It splits, in the process of splitting, some of that mass is transformed directly into heat. That's what we're going to use to make electricity, kind of like a coal burning plant.
Yeah.
But it also releases neutrons, and we can use the excess fast neutrons that aren't needed for splitting extra uranium to breed plutonium.
Fast neutrons can split uranium, but the probability is less. But you need the fast neutrons to convert uranium-238 into plutonium-239. Another reason for the higher enrichment.
Nuclear power is intimidating for people to understand, myself included. So as a result of that,
I think the reason why it's so intimidating is because it requires knowledge base that a lot of people typically didn't go down that path. I don't necessarily think it's any more difficult than anything else I've learned, but if you didn't have an interest in it, take certain classes, then yeah, there's a fair bit of prerequisites and hurdles to go over.
I have spent a lot of time with flannel and googly eyes and 3D printing some stuff, and we're going to take a stab at understanding this. Okay, so Andrew said there are two things going on at EBR-I. He said there's heating, and he also said there's breeding. These are two separate things. Heating is how we make the electricity, so let's focus on that right now. We'll talk about breeding later. So how does a nuclear power plant, in this case EBR-I, make heat? Let's start with a very important atom. It's uranium.
Hot rocks make water boil, basically.
235, and in this little example here, all the protons are red
on there?
and the neutrons are blue. I want to introduce you to our hero. This is a fast neutron.
I like that he made the nucleus look all oblongy.
And when you see this fast neutron, I want you to think of this. Wee, wee, wee. It's so silly, but this is what makes nuclear power possible.
Well, their energy is over 1 mega electron volts, which in pure speed figures out to a few percentage points of the speed of light.
So we've got this fast neutron, whee, hitting uranium-235. Now, one thing to remember about uranium-235 is it's about 0.7% of all the uranium in the environment. The rest of it, 99.3%,
yeah.
Those are all different isotopes of uranium. So when this fast neutron hits uranium-235, it's not like a billiard ball ballistically like blowing up all the protons and neutrons. It's a different thing. It fundamentally changes the nature of this atom, and it's no longer uranium-235. It turns into uranium-236. Now,
it does, yes. Uranium-236 does exist. Not for very long, but it does.
I've got these different color googly eyes to represent the fact that uranium-236 is a little bit different. It's spicy. So uranium-236, really deep on the periodic table, there's a lot of forces at work. It doesn't want to hold itself together.
Well, yeah, you got a whole bunch of positive charges right there. It's going to want to repel each other. That's actually why when you get to these heavier elements, they have a lot more neutrons than they do protons, because the neutrons can act as somewhat of a barrier and allow for the strong nuclear force to hold the atom together, rather than it being, pushed away by electric forces, the Coulomb force. There's a few other factors. One is just simply geometry. I actually like that he stacked a whole bunch of them on top of each other, because it isn't this nice little round, perfectly symmetrical neutron-proton distribution. It does get to a point, at least for uranium-235, where it's stable. I mean, technically not 100% stable, but something with a half-life of hundreds of millions of years, that's pretty stable in the grand scheme of things that are radioactive. But I like that he just kind of stacked them all on top of each other. That's funnier and more realistic.
It's not as stable as uranium-235. So this exists for a very short amount of time, and then something interesting happens. It actually splits. This is fission. It splits the atom into two new atoms. This is not a chemical reaction. This is fission. We are splitting that atom into two new atoms, and they're very surprised to exist. Of course, they are different atoms. We've got krypton and we've got barium.
Note that that's just one instance of fission. It doesn't always split into krypton and barium every single time. It's a distribution. Looks like this. Nuclear engineers call this the Dolly Parton curve for highly scientific reasons, of course. And you can see for uranium-235, the red lines, it's got peaks of things with atomic mass of 95 and things with atomic mass of about 135. And it's a spread. And it's different depending on what you're fissioning. You see, for plutonium-239, it's a little different.
Okay, so these new atoms exist, but the act of splitting that atom has a byproduct that's very, very important, and that is heat. So I'm going to add heat to the board here. So we've created two new atoms, and we've created all this heat. And if we're clever, we can use that heat to create...
This is great for anyone, any introductory to nuclear physics, high school, middle school even.
Electricity. But there's another thing that happens as well, and it's going to take me just a second to get all my heat on the board here. So we've got these new atoms, we've got all this heat, but there's something else that happens. We actually create 3 new fast neutrons, or I guess they kick off of the fission. So you've got these fast neutrons go...
And they do start out as fast neutrons. They can be slowed down, but this EBR doesn't do that. It wants them fast. But in a commercial nuclear reactor today, water is going to slow down the neutrons, so they increase the probability of fission with more uranium-235, so that's why you can get away with less enrichment.
Going off into space, wee, 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 they're just flying off. So everything you see on the board here was in that uranium-235 atom when it was hit by one fast neutron.
This also all happened in less than a fraction of a second.
So if you think about it, we can think of that uranium-235 atom almost like a spring-loaded mousetrap. It's got potential energy and it's stored up, and it's even got these 3 extra fast neutrons over here. And when you hit it, it'll spring off and it'll do crazy things. So if we think about that, and then we cleverly arrange a bunch more uranium-235 atoms out here around that initial fission event, then we can do a really cool thing. With that fast neutron that's kicking off the splitting of the atom, it can go over here, and if there's another U-235 atom in the proximity, it can slap it and trigger it, and then you create this.
That's actually a better analogy than I was expecting. Okay. Yeah. So that's what it is. There are a whole bunch of mousetraps sitting on the planet for billions of years, and yet no intelligent life figured out how to activate these mousetraps. And I also like, because a fast neutron, it's less likely to basically get caught by the mousetrap, which is why a thermal one that's slowed down, it's easier to hit your target, which is, again, why you need more uranium-235, because there's basically a lot more mousetraps in there that it could possibly interact with. That's the thing when you're operating with fast neutrons, you need to set out a lot more traps to catch the faster animal.
This whole thing all over again, creating heat and 3 more fast neutrons. So by cleverly...
Yes, and by counting the number of wheeze from each fission event, and whether it's going up or down, if the number of wee noises you hear is the same, then you can say your reactor is critical.
Arranging U-235 atoms around each other, scientists and engineers can create more fast neutrons from one fast neutron triggering a U-235 atom. It's almost like a bunch of mousetraps ready to go, and if you cleverly arrange them, you can create heat at the rate that you want. So by controlling the proximity or the probability of the interaction of these fast neutrons with these other U-235 atoms, scientists and engineers can control how much heat is created in the reactor.
And it just looks like a game of Scrabble. That's also why enrichment typically isn't uniform in a reactor, because you're trying to make something uniform and perfect, which would only work if the reactor is in the shape of a sphere and you made spherical shells, which are a pain to engineer. But no, Scrabble board, and with fuel assemblies that look like this arranged in a cylinder. It's just why you got to vary it a bit to achieve a more uniform and optimized heat profile and radiation profile.
Which is amazing. And we're going to learn more from Andrew as we learn more about the plant, but I have some more felt stuff later that has electric motors attached to the board, and I think you're going to enjoy that.
Electric felt.
What's your deal, Andrew?
He's going to use the felt to generate static electricity. Is this guy also like Electroboom? I've never seen any of his videos before.
A student? What's your deal, man? I got to know.
So I'm a mechanical engineering student.
Yeah, you
I just
are.
have a deep love of history, so I
Okay, so he's a mechanical guy. All right, cool.
wanted to work out here, get some public.
Where I went to school at Georgia Tech, the nuclear engineering program was actually underneath the mechanical engineering program, because a lot of the thermodynamics, hydraulics, fluid dynamics classes I took were prerequisites to some of the more advanced reactor theory classes. So it makes sense that it's relatively easy to transition from mechanical to nuclear.
Outreach before I'm stuck behind a desk.
You're not going to be stuck behind a desk being a mechanical engineer. You're going to be...
You can be. It just depends on what kind of job you want, but you don't have to be stuck behind a desk at all.
building awesome things, man, like reactors.
That's true. I'm more meant just... I get to talk to people and interface with the public while I'm out here, because there's so many misconceptions around this tech.
He's very good at that. He has the voice for it, the knowledge for it, and I don't know, just something about the presence for it. I mean, like I said, I could tell right at a glance that he was going to be a good guy.
Technology and its safety, but this is the first reactor ever really made to produce electricity, and it has a bunch of inbuilt safety features that most people wouldn't have even expected.
Is this how EBR-I worked?
Yeah, essentially.
So 3 interfacing loops.
Reactor, and then that's liquid going through there.
Yeah, it's a
Notice it's not pressurized.
liquid metal. It's a bit unique compared to most modern designs. We used a mixture of sodium and potassium. It's a liquid metal eutectic, which means if you get the right alloy, it has a lower melting point than either of the base elements. In this case, like mercury, it's liquid at room temperature.
Well said.
They had to use a liquid metal because water absorbs and slows down neutrons, and they needed fast neutrons to produce plutonium. So they had to find a way to make the liquid metal work, and that's why the system looks a bit weird. Technically,
Yeah, it usually goes like from here to here.
Yep.
Yeah, and you don't have this loop right here.
And technically, to make this function, you wouldn't even need this middle loop, but it's there for a pretty good reason. If you were ever to have a breach between these two pipe systems that allowed the two coolants to mix, you'd get a pretty big explosion. The alkaline liquid metal will basically rip the hydrogen off the oxygen in the H2O, so you do get an explosive reaction.
Yes, sodium is very reactive.
They would not want that to be highly radioactive. So by splitting up the liquid metal loops this way, the highly radioactive coolant is sequestered in this first loop.
Very well said. I mean, yeah, you're basically having another wall of liquid metal that's getting less neutron dose because you double the distance from your source. The dose is going down by a factor of 4. And when neutron interact with metal, they can activate them. Basically, the sodium absorbs the neutron and then becomes radioactive sodium. And that's one of the disadvantages of using liquid metal in general, but they have a second layer of less radioactive liquid metal because it's with it being separated by not only distance, but a heat exchanger, so shielding as well. Not to mention, metal itself acts as a form of shielding, though against neutrons less so, but still, the point is, the intermediate loop you see here is significantly less radioactive than the primary loop.
Provides one level of safety. There's a second level that exists in the secondary heat exchanger. We'll talk about that downstairs.
All right, Andrew did a great job of explaining everything, but selfishly, I just wanted to build it and play with it to understand it better. So that's what we're going to do. The first thing I want to talk about is the fact that they use liquid metal.
I like his attitude.
That's a pretty big deal. So I purchased some gallium, which is a room temperature liquid metal that you...
Thanks for not just playing with mercury like that. I mean, you don't want to drink that stuff, but it isn't mercury. And it's also not reactive like just taking liquid sodium or liquid potassium, or God forbid, something like cesium.
You can just buy and play with. It's really fun to see a metal flow like a liquid. But why did they do that? That's a really strange design choice. So the fast neutrons, when they kick off of a uranium-235...
I mean, the short answer is you want good thermal conductivity, but you don't want to moderate the neutrons in this particular design. Whereas You just use water in a commercial nuclear power plant, so that's another advantage of just pressurized water reactors is you don't have to, there's less engineering involved, less complexity.
Atom. Those things are going 14,000 kilometers per second. Very, very fast.
So yeah, small percentage of the speed of light.
The thing about fast neutrons is when they go through water, they slow down. So,
and by the way, that 14,000 number, that I think that figures out to right at 1 million electron volts. For a sense of scale, a thermal neutron or a not fast neutron is less than 1 electron volt. And they do have a range, so there's probably a speed. The speed range is going to be on the order of, in kilometers per second, it'd be 5,000 to 30,000. But a lot of them are probably going to be centered around 1 mega electron volt.
If you have just water like this, there's a bunch of hydrogen atoms in there, and that fast neutron will interact with them, and it'll slow down to 2 kilometers per second. That's not good if you want to use this.
Not sure where he's getting that from. There's nothing magical about 2 kilometers per second. I mean, yeah, it'll slow down to that, and then it'll slow down in fission.
As a breeder reactor, which is what they wanted to do. So there's this other material called NaC, sodium and potassium. You can see how it gets its name right here. Na for sodium, K for potassium. NaC is not a moderator. I've never
referred
like
to as
so
that.
The fast neutrons will,
and I don't know why, because that's hilarious,
just zip through this. And it's also a really good conductor of heat. So it makes an ideal liquid to transfer heat away from the reactor. So the first 2 loops in EBR-I were NaC, and the third loop was water. Now, just like Andrew said, that first loop is isolated from the second loop, so that if you did have...
Oh, I just realized he actually filled them up. I thought it was just another felt thing. That's awesome.
NaC come in contact with water, because that doesn't work well. It'll explode if that happens. If you have an explosion, you don't want it to be a radioactive explosion. So you isolate all the radioactive stuff over here in loop 1, and then, well, let's just see, how do we get heat?
One thing they're going to have to look at is they're going to need to have there's also going to need to have more radiation monitoring just in that intermediate loop, because you want to see if you have a tube leak from primary to intermediate, and then you're still going to want radiation monitoring at the final, the secondary loop to monitor for what would be a double tube leak. Now, I'm not saying it's bad to have 3 loops. I mean, it overall is a good choice just to minimize that risk, but it's just going to be that much more expensive compared to, say, one that uses water as your coolant and a moderator and isn't a fast reactor at all.
Heat from the reactor all the way over there. So let's look inside of our loops here. You see there's our reactor. That's just a heat exchanger. That's a heat exchanger with some steam in it. Okay, so
the other disadvantage of this is the heat's got to be transferred all much further. And while NaC, I'm going to call it NaC now, is a better heat conductor than water, it's still, you're using more NaC, and it's still going to lose a little bit of heat as it goes through that intermediate loop. That being said, liquid metal is better at natural convection. So these little pumps, if those were to fail, it's going to circulate faster than the water loop if it was to fail. I've done drills and cool downs in a pressurized water reactor using natural circulation. It's a lot slower. The loop transit time in a primary loop is usually on the order of 10 seconds, but that's with a powerful reactor coolant pump. If something were to happen to your pump, it's much slower, and the reactor just takes that much longer to respond. Your 10 seconds is going to turn into 20 minutes. Not saying it isn't safe, it's just going to be a slow cool down.
Let's look at how this works. So I've got this little setup here. I've got a little distribution panel so I can turn things on and off. I've got a bunch of motors and stuff behind the board there. I'm going to show you how this works. So first of all, let's turn our reactor on. I'm going to take this and move it up, and we'll understand why that turns the reactor on later. So our reactor is now running, and
he's simulating is he supposed to simulate withdrawing control rods?
We are creating heat inside the reactor.
Oh, this is
the problem is if we just keep making heat over and over and over and never do anything with it, it'll just sit there and melt everything down. So we have to move the heat away from the reactor.
I mean, continuous heat input with zero heat removal, sure. I guess if he was talking about if this was some isolated closed loop, it'll heat up Now, whether or not you'd melt down or the system would overpressurize, that's debatable. Depends how you designed it.
And the way we do that is with NAC. So we're going to turn this little pump on here, and we're going to pump NAC through the system through this heat exchanger. So that gets us to the second loop. So the interface between loop 1 and loop 2 is basically a pipe within a pipe. That's a heat exchanger. So they're mechanically isolated from a fluid perspective, but they're not thermally isolated. They're actually thermally coupled. Pipe within a pipe, that's a heat exchanger. And once we get here, we can just simply turn on another pump here, and we
note that they're thermally coupled but not hydraulically coupled, so you're not getting your radioactive primary loop into your intermediate loop, or if you do, you have a leak.
Can pump the heat over to the third loop. Now, the third loop is important because we have water in there, and when you heat
I like that he's intentionally using smaller heat lines, because heat does go down as it's got to be transferred through this whole thing. It's a good conductor, but not an absolute perfect conductor.
Up water past a certain point, as you know, you make steam. That steam can be converted to mechanical power. So we're going to take thermal power, move it all the way down, and convert it to mechanical power.
Note that the intermediate or secondary loop have nothing nuclear about them. I mean, I guess you can argue the intermediate loop as a buffer because it's a nuclear plant, but the secondary loop, the water loop, that's been around for a couple hundred years.
By activating this turbine right here. So at that point right there, we can use that to turn a generator and all kinds of things like that. And as this
Okay, on the note of the turbine pronunciation, he says it the same way that I do, so he must be from the same part. He must be from a similar part of the world as me. I've noticed there's been a few discussions in the comments on turbine versus turbine. They're both acceptable, by the way.
Steam goes through the turbine, it loses energy, and we can condense it back into water, and we can send it back into the loop. We can just use this loop right here over and over and over. And if we hook a generator up right there, we can actually create electricity. So that's what we're going to do right now. Let's hook.
Know that if you didn't have a generator, the turbine would just have a bypass that would send that steam back to the condenser. And any system like this, whether it be a nuclear plant or a coal plant or a natural gas plant, their condenser would be designed to accommodate a full load reject from the grid, and the condenser could take all of the excess steam that would be sent there when you pump the brakes without any issue.
Up our let's just hook up those wires, and there we have it. Light. We have done it. We have created the world's first nuclear power plant. We've gone from nuclear power, thermal energy, all the way to electricity. This is the world's first nuclear power plant, EBR-I. And remember, this is a...
Note that he says power plant. There have been several reactors before, some deliberately designed just to make plutonium for weapons, say during the Manhattan Project. But this one makes electricity.
Fast reactor. There's two types of reactors: a fast reactor, which uses fast neutrons, or a thermal reactor, which uses a moderator which slows down the neutrons. That's not what EBR-I was. And the reason they wanted a fast reactor is because of the breeding process, which we'll learn more about later from Andrew.
They wanted to make plutonium.
But now that we know how all this works, let's go learn how they controlled it.
All right, let's take a look at the control room next.
Let's see how it compares.
I love your tour style, Andrew. It's great. You've refined it, haven't you?
Yeah, I've had a bit of practice out here.
All right.
Oh, look at this.
Is this control room?
Yep, this is the control room.
Is this where originally, this is the original control room?
Yeah, essentially everything in here is original. There are a couple of pipe systems I've noticed throughout the building that changed as they updated the reactor core, but that's basically it. Everything else is in the position it had started in the 50s.
So primary coolant was metal.
Yep.
Right? All of this. These are measuring the temperature.
And I love these.
I like the gauges are nice and big. In control room, the control room I worked at still had a bunch of analog stuff. Even that paper chart recorder right there. When I first hired in, we had one more of those, and then it was retired, which was actually what logged what step the control rods were at. And I got qualified as a senior reactor operator in the 2010s. So yeah, and this is from the 1950s. Now, granted, we had a lot more computers, and we had the computer equivalent of just about everything else. But don't underestimate the analog gauges, because they will actually respond slightly faster. Because they're analog, there's no lag for a computer to try to calculate something. So if you're an eagle-eye reactor operator and you can almost see something coming, it's possible for you to pick something up before the plant computer does, especially in the simulator, because that's a video game that has lag associated with it.
These paper graphs, they measure time radially, so 24 hours is a full circle, and amplitude is measured from inside out. It's so simple and beautiful, and it makes perfect sense if they had to switch these out every day.
Yeah. Do you have any of the old blanks?
I like how big they are.
I don't know if we do or not. I'm sure that they exist somewhere, but I don't have access to them.
Okay, so here is an actual drawing. Yeah, you can see it.
The chart recorder.
It's pretty cool. Oh, midnight right there. Midnight. So what time is it right now? It is 2:30-ish. So midnight would go 2:30. So right here, that is the temperature at that time. I just don't know how to measure it. Okay.
Yeah, they're a bit hard to read, but there is something really nice about these old systems. I've had some old nukes come through, and they tell me that with this sort of very analog way of recording data, it can be really intuitive for the human brain, because you can look at the circle and see what portions of the data are larger or smaller as far as amplitude goes and read it very quickly.
Again, especially the size. Yeah, and that's good for making quick big picture decisions. There are some gauges, and it would be something like reactor coolant temperature, obviously reactor power output expressed in percent or megawatts, that would look at. Now, some of these, again, would be computer screens in addition to analog gauges. No, unfortunately, I can't show you pictures of that, but I can still see it has the same general design philosophy.
In a modern digital system, you'll have maybe a catalog of 10,000 entries for whatever the amplitude is you're recording.
Yeah.
And oftentimes, that's harder to understand for the human brain than looking at something like this. You can pick trends out a lot quicker with this.
Okay. Another thing is a lot of the important ones are time averaged points, which again underscores that some of these analog things can get you information faster.
This is amazing. This is incredible. Oh, God.
Those little graphs.
They like hand calibrated.
And you'll see these notes all throughout the facility. Basically,
just looking at the handwriting style, looks very different than any reactor operator I've seen. Sometimes I'd need to do some deciphering.
Every system, they were learning for the first time. So as they figured out how to do it, they'd write notes so that the next person to do it basically had a baseline to work from.
So this is incredible. So what they're doing is they're calibrating. So they have an analog measurement here and tank level in inches. And so this is the curve. And so this is how to read this. So if I said I've got 2 amps, I would say 2 amps. Oh, that is 30, 35.
And just a basic level indicator. Yeah. It just gives it to you. That's super old school. And there are some things that you do that at a commercial nuclear power plant you still do, whether it's in amps or if it's an air signal in PSI, and that corresponds to level, temperature, valve position, whatever, reactor power. There's one reactor power, if you're at the intermediate range detector, that it's still given in amps. And of course, there's an equivalent of what percentage power you're at.
5 inches is how much fuel is in my tank, or whatever this is in your tank. Primary drain tank. Okay. I appreciate this so much. I used to do instrumentation, and one of the first things we would do is we had to make the curve for your instrument. And you kind of set the low end and the high end, and then you figure out how it all works. I've never seen that technique, and it's awesome.
And I like these little operator aids. They're just written on the board like that. You still see some of that sort of thing sometime. But yeah, making sure that sort of stuff is calibrated correctly and, the right amperage corresponds to the right number is a pretty big deal, because a lot of these things can feed into things like automatic reactor trips. So you want to make sure that sort of stuff is accurate. Have really good I&C techs, that's instrumentation and controls. And there's an expression, if they try to fix something and it doesn't work, and they say, well, let's just try and see, not I&C.
I'm sorry. That was a little too much geeking out there, Andrew.
Oh, believe me. I'm all for it.
Okay, that's awesome.
I like these guys.
So then there's
sound like my
one
kind of
particularly important button I always like to talk about, and that is, of course, the scram button. If I pressed this while the reactor was operational, it would be shut down in about 4 seconds. From the beginning of these
4 seconds. Not the best ever, but not awful. Chernobyl apparently took like 30 seconds. Control rods are tested, and at the plant I worked at, it was more like 2.
reactor designs, they knew they had to be shut down quickly if the power was rising quicker than they could really ameliorate it in another sense. This system has 2 different ways of scramming. One of them would insert the control rods all the way in, it would slow it down over time, and then it was ready to start up immediately. The other scram system, which was I think pulled from this pulley here, would drop the outside blanket, immediately decreasing the reactivity to 0, and that—
Oh, like 2 different methodologies. I was thinking like 2 different signals. There's probably a handful. The plant I worked at had more than a dozen.
would shut it down immediately. The only problem is they could not start back up quickly. They'd have to go through a process of making sure the blanket was good to go. Took about an hour before they could fully restart it.
So that's a serious scram.
Yep.
So this is the more graceful scram, and then this is the oh heck.
That's the we need to have all of the shutdown margin in the world sort of thing and take some time to get rid of. There's a version of that, and that's mainly if the regular scram or reactor trips, the term I'm used to, it means the same thing. All control rods insert immediately. And the equivalent of that at the plant I worked at was what's known as emergency boration. So boric acid, basically liquid control rods, and concentration is kept anywhere between 1,400 and like 20 parts per million, depending on where you're at in core life. So throughout core life, you gradually dilute it as you use up all of your reactor fuel, because boric acid slows down the fission reaction. But you're using less fuel, so unless you dilute it, the reactor is going to shut itself down eventually. But emergency boration, where if, I don't know, reactor trip somehow didn't work, which would require gravity to fail, or maybe a massive earthquake that caused the control rods to not insert at the proper angles. Even an earthquake, I don't think, would do that, considering how quickly they would fall. But anyway, as a backup, boric acid pumps can inject directly from the boric acid tanks, which are kept at a concentration of over 7,000 parts per million, which is way more than you would need to have something that is shut down. To give a sense of scale, the spent fuel pool is kept at a concentration of 2,800 parts per million, which is already way more than enough.
Let's grab that ring and pull it.
And it used to hang down a lot further, but kids thought it was fun to swing on, so.
Oh yes, it goes
Absolutely.
up. Oh, that's interesting. And so it's in the middle of the room, so anybody can
I've never seen anyone bring their kids into a control room.
pull it.
Yep.
Okay. I could spend too much time in here, so should we go to the next place?
I could too.
Time to talk about breeding. Now, breeding is a
Birds and the
very
bees.
special thing. We can make nuclear fuel from nuclear fuel, and it starts with a uranium-238 atom. You remember when we were talking about uranium-235, this is about 0.7% of all.
When a uranium-238 atom and a fast neutron love each other very much, okay, maybe not,
the uranium you'll find in the world, whereas uranium-238 is more prevalent. It's about 99.3%. Now, when we did the fission thing earlier, and we kicked off, these little fast neutrons, when a fast neutron comes in contact, with uranium-238, that creates uranium-239. You can tell from his eyes that he's just a little bit spicy, right? So the uranium-239 exists for a while, but then about 23 minutes later, give or take, we have a really interesting thing that happens. We kick off an electron.
The point is, this is way slower than... So when you're operating at steady state, it's not like you have to wait the 23 minutes because this is already happening. But the point is, this reaction is far slower than a fission reaction, where it's a fraction of a second.
And we have this process called beta decay that happens inside the atom. Some neutrons and protons, they switch roles. It's kind of strange. And then we end up creating
Basically, uranium-239 is unstable, but it's not nearly as unstable as 236, where it wants to just split in half and spit out neutrons. It could actually split into more than two pieces, by the way. That's known as ternary fission, but the third piece is usually pretty small, like an alpha particle. But this one is, well, I just need to get a little bit more sloughed off to be stable. So I'm going to go ahead and beta decay a couple of times.
As a result of this beta decay, Neptunium-239, completely different element. You can tell he's very different. So after this time, we have another beta decay event. That beta decay event happens around 2 to 3 days later. We kick off one more electron. We have some stuff happen in the nucleus again. And then we create the ultimate spicy element, which is plutonium-239.
So I guess by spicy, he's referring to the potential energy it releases, not how quickly it decays, because it has a half-life of over 20,000 years.
Comes into existence. Now, the thing about this process is you're making nuclear fuel from nuclear fuel. And in fact, you can make more atoms of plutonium-239 than you put in to begin with of uranium-235, which is a very special trait for a nuclear reactor to have.
So as earlier, this whole process occurs in a non-breeder reactor. And the end result is, towards the end of a fuel cycle, you're fissioning north of 20% plutonium. So you mentioned spicier. Plutonium releases more energy. Plutonium-239 releases more energy than uranium-235. Now, reactor power doesn't go up because all the systems keep its steady state at 100% power. But what it does mean is any changes to reactivity are faster.
In order to do all this, you have to get a fast neutron to hit the nucleus of a U-238 atom so it becomes U-239, but that doesn't happen all the time. Sometimes these fast neutrons bounce off, and the engineers and scientists that designed EBR-I used that to actually run the reactor.
It's all a big Monte Carlo simulation. Everything with radioactive decay, to fissions, to absorption, to moderation, to breeding. It's all a Monte Carlo.
It was pretty interesting what they did.
Let's head out this door and see the reactor itself.
What?
Very close by.
This is it?
Yep.
Oh, an over
It doesn't
reactor.
look like much, but this is a relatively small reactor. So right now we're...
I wonder if they're going to have over reactor bungalows. I like over water bungalows, which... in most cases, an over-reactor bungalow would be an over-water bungalow, but this one not the case. It'd be an over-NAC bungalow.
Standing on the radiation shield for the reactor. I would call it a containment vessel, but technically they're a bit different. Containment vessels are essentially meant to hold in the products if they have a meltdown. This is just a big radiation shield. Normally...
Okay, I can definitely tell this guy's for real, because in most... research reactors, experimentals. You could use the term confinement and it wouldn't be wrong to keep certain things in, but when I think of containment, it's not just it won't escape, but it will survive a thermal and pressure excursion, or I should just say explosion, from the inside. And it's rated for whatever the energy level of the thing is that you're trying to contain.
There'd also be a big plug right here that would prevent radiation from coming out of the core, but now that it's been decommissioned, they can safely take that plug out and let us look inside. The core itself is just below that machinery. We'd feed fuel rods into it through that machinery, and the core is set up using these hexagonal assemblies. The center 7 contain the uranium-235 that's propagating the chain reaction, while the outside ring of hexagonal assemblies contains 238 to breed plutonium.
If that entire honeycomb structure was filled up and 14 feet long, that's the length. That would be about the size of one fuel assembly at the power plant that I worked at, and there were 193 of them, though there were square.
There's not uranium in all 10 feet of these rods. It's only in the 8.5-inch heat zone near the bottom, about a football-sized zone. That's where all that reaction would take place.
Sure.
For this particular reactor, they operated using about 60 kilograms of fuel, and that means that there wasn't enough for it to go critical by itself. That's why this outside breeding blanket was necessary. It acted as essentially a reflector. It's made of 84 bricks of uranium-238. They're set up in this cup shape.
So no moderator, but it does have a reflector. Now water does also act as a reflector in at the power plant I worked at. It's exactly what you think it means. Things that keeps the neutrons from escaping the reactor.
On an elevator just below the reactor core. The hydraulic elevator would bring that up around the core when it was ready to turn on. It'll reflect neutrons back inside and give you enough neutron flux for the reaction to occur. So we didn't use control rods for startup and shutdown. We used this for startup and shutdown.
That blanket. Mm-hmm. Okay, remember our...
Now what's interesting is that the plant I worked at, we used control rods for startup and shutdown, and definitely shutdown, but during startup, the reactor engineers would just set the rod height that they wanted, or they knew that we wanted to start the cycle at, and we would just dilute to criticality. So we'd have a higher boric acid than we'd need. We'd withdraw the control rods, which adds positive reactivity, but not hot. But the control rods by itself wouldn't be enough to start it up, and then we would just dilute the boric acid in the reactor with just demineralized water until it reached criticality. Now, we'd still move control rods when we raised power, but initial criticality, which occurs at less than 0.001% power, no. The main guy, and that's perfectly safe, the main thing to stay away from is when you're below 1% power, do not add positive reactivity, which is ways to increase reactor power more than one way at a time.
Board with all the stuff on it. I'm going to put you on this tripod right here so we can look at how to start up and shut down the reactor. All right, so let's check it out. So as we raise the blanket,
we start
the nuclear reaction. And to stop the reaction, we just drop the blanket. That's how this works. So we have a physical control now for nuclear power, and that's how they came up with that. And to explain what exactly is going on there, I'm gonna have to change out the board to the other board. So let me do that now. Okay, let's build the reactor from the top down.
Oh, I just got a really cute Valentine's Day idea. You take your U-238 felt guy, your fast neutron, and you have them cuddle together under the blanket, and then you make a 239.
So over here on the right, this is the top-down view of the reactor. The red is U-235 enriched. The outside is U-238, okay? Over here, we've got the U-235 atom and the U-238. So this is like the conceptual model. This is the top-down view of the reactor. So let's look at how this works. Okay. So when we get a fission event from U-235, we're kicking off those 3 neutrons, right? Those 3 fast neutrons. Wee, wee, wee! They're flying out here. They're going really fast, right? Sometimes they will interact with the U-238 and you might get breeding. So that.
By the way, the average number of neutrons from fission is about 2.5. So him showing 3 is actually pretty cool because a lot of times you only see them people show 2.
If you look at it over here, that would be leaving U-235 and interacting with the U-238 atoms out here in this inner blanket, they call it, right? So when it does that, sometimes it'll create plutonium. Sometimes it'll bounce it back into the U-235 to sustain the fission reaction. However, because of the arrangement, sometimes these neutrons, they don't hit anything and they just keep going. That's what the blanket is for. If we were to put a neutron mirror, let's think about it like that right there, and on the top-down view like that, then this is what happens. So if the fast neutron flies, it misses the U-238 and it keeps going and it hits this big wall of U-238 atoms, right? These bricks of U-238. It hits this wall, it reflects, then it will bounce back and that...
It will also moderate it a bit too, which is why water is a good moderator and reflector. It's not a perfectly elastic collision.
Increases the statistical probability that it's going to hit a U-235 atom. So your chances of sustaining a fission reaction goes way up because you're getting 2 shots with those neutrons, right? Well, maybe not 2 because some of them just keep going, but you get the idea. So it leaves the inner core. It goes past the inner breeding blanket, which is cooled by liquid metal, NaC, if you recall, and then it goes out to the outer breeding blanket, and then it sometimes will bounce back into the core. That's why applying, like if I did this, then it's very unlikely that it's going to bounce back. But if I did this,
then we're going to bounce neutrons back into the core. That's why raising and lowering the breeding blanket is so important, and that's why they could turn on and off the reaction. If they balance the amount of U-238 and where it is and how many neutrons can go where, they can just flip a switch and turn on or off the reactor, which is fascinating.
So that would come up and down?
Yep. Originally, they had it set up so it could only be fully up or fully down, but they realized that that wasn't ideal, so they added in some hydraulic control systems so you can get more fine tuning. And this is also where our control rods would go into. So we did have 8 control rods, but they'd go into the outside blanket for fine tuning. As the reactivity of these rods decreases over the 9-month lifespan, they'd pull the control rods so they could get the same power out.
So the outer blanket would move up and down?
Yes.
That's the same principle with the whole boric acid dilution in the power plant I worked at. Now what's interesting is that had such an impact. Control rods were kept at pretty much the same height an entire fuel cycle. Like you might start out with the outermost bank at 230 steps and end up at 245 steps after an 18 to 24 month cycle. But the main reason why you moved rods in that reactor was to change the axial flux distribution. So the reactor is cylindrical, and what axial flux means is whether reactor power is being produced at more at the top of the core versus the bottom of the core, because it's not symmetrical. So control rods, since they're a rod that comes in and blocks a certain percentage of neutrons, would have a pretty significant impact on axial flux.
Sir.
And if it comes up, what happens?
If you bring it up, it'll increase reactivity until eventually you reach criticality and the reaction starts.
Because it's reflecting neutrons back in towards the fuel.
Yep. And this is also breeding plutonium. That's why it was made of uranium-238.
Okay. So you have to lift it in order for it to activate, and so gravity is your friend.
Yep, and that's why our scram system works in an incredibly simple way. When they scram this facility,
a good engineering principle is try to avoid designing systems where gravity is not your friend, because you're going to have to deal with it.
Then dropping control rods into the core, which is how it works for almost all modern facilities, it'll empty the hydraulic systems that hold the breeding blanket up and drop that down into the basement.
So it just opens a valve?
Yep.
Okay.
And that would shut it down in about 4 seconds, but it would take an hour to restart if they scrammed it that way. That's why they had 2 separate scram systems.
Are these actually
an hour to restart? So could you restart a commercial nuclear power plant in an hour? No. Could you physically do it? Within an hour, you might, if it's an uncomplicated reactor trip where nothing breaks or anything, you'll finish your reactor trip response procedure. But ultimately, investigation, find out why the reactor tripped, getting permissions from management team, engineering team, recommendations. Depending on what caused it, there might be some regulatory approval involved. I'd say a quick restart is a couple of days for a commercial nuclear power plant. And that's because you've got to coordinate it with the grid and everything. Syncing a 1,400 megawatt generator onto the grid it takes a little bit of coordination, not a ton, but the point is you're not restarting it within an hour.
Actual fuel rod assemblies?
I think these are just mock-up assemblies and rods, but they are all exactly the size of the originals.
That's cool.
That makes sense.
And there was fluid in there, I'm assuming. Was there water?
Dummies.
Not water. So this would be the liquid metal cool part of the system. Right up here on top under the plug, there would be a layer of argon gas. That would prevent oxygen from ever getting down into the coolant. It could ignite the coolant if it comes into contact with air due to the oxygen.
Yep.
So this would be filled with argon, and there's argon in a couple of our other systems that we'll see as well.
Is argon heavier than air?
Yes, significantly. We use argon for similar purposes at the power plant that I worked at. I believe its density is like 1.4 that of air.
Yeah, I believe so. And for the case of argon, it acts essentially as a noble gas that's completely non-reactive. That way you won't have anything reactive come into contact with the coolant.
That's awesome. That's cool. Where to now, Andrew?
All right, let's go take a look at the generator where they powered the first light bulbs to ever be powered using nuclear energy.
Look at this.
That's not actually true right now, is it?
Not anymore.
So that was true at the time, though, right?
Yeah,
That's
and it was
fun.
also a huge point of pride to the men working here. It's important to remember
Also calling it atomic power, that's very 50s.
that they had just come from the Manhattan Project, meaning their work had recently been used in Japan to kill thousands of civilians at Hiroshima and Nagasaki. Whether or not it was the right choice to drop that bomb is not something that I ever pretend to know or tell people. That's not really something I can decide because I wasn't there at the time.
Come on, Andrew, I'm putting all of that on you.
That's not part of this video.
But really, they cared about producing power. They knew
Maybe talk about that in a different video.
this could be an energy future for the world, and it mattered to them that they were on the other side of that coin. That sign was a point of pride because of that. From what I understand, they would never turn that sign on unless the reactor was producing electricity, and they would shut that off before they shut the reactor down every night. They really did care about that being true.
Is he taking a breath?
They cared about it. That's awesome.
Okay, there we go.
It was almost like plowshares. You're familiar with the verse in the Bible, beating their swords into plowshares?
Yes.
Have you heard of that?
Swords to plowshares.
Yeah, the Plowshares Project. And so, that was a whole
Wait, is he talking about using nukes to dig holes?
different thing for people. That's great.
I see what he did there, a whole different thing. Also a topic for another video.
All right, next we'll head out to the generator. So a reactor only has one job. In the case of EBR-I, it's got two, to produce both heat and plutonium. Through our heat exchange system, we boil water, we send the superheated steam up through the back of this turbine to spin it up, then through the
so
gearbox,
old school.
the generator is spun up even faster to produce
But yet at the same time, very familiar.
electricity. On the
This is the gearbox?
Yes, sir.
Okay.
On the 20th of December 1951,
like
for
how
the first
small
time, they had
everything is.
all their systems in place. They had been turning on the reactor since about August, but they were finally ready to make electricity. On that first day, Dr. Walter Zinn, the lead for the project, wanted to start small, so he just strung up 4 300-watt light bulbs, connected those to the generator,
300-watt
and when they
light
turned the
bulbs.
reactor on for the first time to produce electricity using uranium for the first time, they just powered on 4 light bulbs. The next day, they connected it to the rest of the facility, and it would power the whole building going forward.
That's amazing, but this was the moment.
Yep.
Is this a photo of the moment?
Yep.
Really?
Afterwards, Reed Cameron thought that they needed to commemorate the occasion, so he got out a ladder
That's a
and
good-
some chalk. He wrote this excerpt up on the
like
wall,
that.
and everybody signed their names underneath it to commemorate the event.
That's the original?
Yep. They encased it pretty soon after they signed.
Electricity was first generated here from atomic energy on December 20th, 1951. On December 21st, 1951, all of the electrical power in the building was supplied from atomic energy. Those present, and those are all the people that participated.
Jolly signed a few days later. He was the local janitor.
Very official. I'll still see things at like the old part of a nuclear power plant where like some of the construction guys sign their names. I'm sure that's pretty common in any facility when it was built for the first time.
Jolly did?
Yep, that's the name on the bottom there. But I think everybody else signed that first day.
So that is a moment. What is the picture?
So Reed thought it looked kind of boring, so he got back up there, he drew the character blowing air on top. Nobody knows exactly what it is.
Just a little
but
doodle.
literature and some of the memoirs from the men who worked here is that they figure it's the devil blowing air, creating energy. And
I was thinking somebody went to Purdue and he was a Boilermaker.
personally, it kind of seems like their way of saying this thing that's been used as a horrible weapon can also be used to create power. But I can't attribute that to anything in specific. That's more of a me thing.
That's awesome. So this would have been
just
powered
been
with
bored.
water. So where are the heat exchangers that take the heat out of the liquid metal and turn it into water?
We'll see those next. They're right below us.
Okay, let's do it.
That makes
You guys
sense.
are filling up. A lot of people visiting.
Given where the reactor was
it
at.
gets pretty busy around this time normally.
Does it really?
So through this door here is the secondary heat exchanger. It might seem like an awfully big system for 45 kilowatts worth of electricity, but that's because it's a safe design, not a spatially efficient design. It's a pipe within a pipe heat exchanger. The innermost pipe carries the liquid metal coolant from the middleman loop. Around that is a pipe filled with argon.
So they're calling the intermediate loop part of the secondary. I guess that kind of makes sense. I've just been calling it the intermediate loop.
Gas, the totally noble non-reactive gas we talked about before. Then around that is the pipe carrying water to be heated, boiled, and sent up to the turbines.
So the heat has to go through the argon?
Yep, that's why it's so big, because argon's not particularly conductive.
Yes.
But the argon's there for a good reason. If you do have a pipe breach on either
But argon's good because it's not reactive, and you want it to be, and you want something heavier than air.
side, you don't want the coolants to come into to mix. That will cause an explosion. So instead, they'll only be able to mix with argon, which is completely non-reactive. That's why you have the jacket between. those two layers. So I always stop here just for a moment. There's not too much to see in here, but this is the primary coolant loop feeding coolant.
All the radiation signs just say special instructions on there.
Right from the reactor. And I do like to note the thickness of this wall. A lot of people have the misconception that these early nuclear scientists would have received high doses of radiation working at these plants. That was true for some experiments that they operated, but not for the plant itself. This wall is 4 feet thick to act as gamma radiation shielding. They knew, based on studies they've been doing in Japan, that they had to shield from that radiation, and you need a minimum of 4 feet of water or high density concrete or 3 feet of lead to mitigate those effects. That's why this wall is so thick.
So that is for neutron dose, which is going to be the most penetrative, even more so than gamma radiation. Gamma, you're probably good at like a foot. But neutron, dense material, hydrogenous such as concrete, that is why containment buildings at nuclear power plants are so thick.
And that's concrete. Oh yeah, those are not concrete. Excuse me, those are not cinder block bricks, they're concrete bricks.
Yep.
Yeah, it's solid.
Okay.
So this right to my
Cinder
left is
blocks
the
would not
cask
be
that
good
would allow
choice.
us to pull spent fuel rods out of the reactor. It's a lead-lined container that helps trap the radiation within. The tank on the back of it fills it with argon so that when they pull the fuel rods, there's no oxygen interacting with the liquid metal coolant. They'd have to pull it one rod at a time, so it was a pretty lengthy process.
So they would put something down in there, grab a rod and pull it out?
Yeah, so basically they'd take this 10-ton crane above us in the corner, they'd hoist this cask up on top of the reactor, and it would sit on this plug, but this...
And that's basically how refueling still works today. Specialized crane. The difference is everything is being done underwater, and these guys are up on a bridge operating the crane. And you need very specialized crane operators to do this. And one person in here is someone from the local site with a senior reactor operator license. I could have done this job, but the crane operator that's basically what they do. They go to nuclear power plants when they're shut down, and when they're done with one outage, they find a site in another part of the world that needs to be refueled. It's one of those jobs where you're quite well compensated, but you don't see home very often.
It'd be upstairs where the hole in the reactor we saw is.
Which is right up there.
They'd be able to rotate this plug, and then through these 3 hatches, they could gain access to the different parts of the reactor and pull just a single rod out at a time.
That's cool.
Once they have the reactor, close up the bottom of the cask and move the whole cask for cleaning and storage.
And so they could just store the rods?
They had to store the rods. The daughter products within them, when you take this big atom of uranium and break it in half, those 2 daughter products are unstable. When they break down, they don't just release radiation, they also release heat. So you have to store.
That's what's known as decay heat. And it decays fairly quickly. Like within a matter of seconds, you're at but a small fraction of full power. Thing is, though, you see here after 10 days, it's 0.16 megawatts. Or 160 times more energy, or 160 times more power than a typical household microwave. So that heat's got to go somewhere and needs to be managed by a spent fuel cooling system.
For them before you can ever do work on them. That way they have time to cool.
Oh, wow. So there's a lot of thermal capacity there.
Oh, yeah.
Fuel rods? Is this where they would store them?
This is where they would store the fuel rods before they went into the reactor.
Okay.
So the vault here might make it seem like you needed a bunch of shielding. Really, the vault's just to prevent anybody from gaining access if they're not supposed to, and for accountability. At the time, we were shipping all of our uranium from Africa. The military wasn't certain that we'd be able to continue those shipments, so they kept very tight track of essentially every ounce of uranium. We'd bring it here from Hanford, we'd weigh it before it went into the vault. If we ever needed, let's say, 3 pounds of replacement fuel, we'd have to weigh it very carefully before we took it out of the vault. So this kind of helps us keep track of all the uranium that we're using.
So new fuel is not hazardous, really. I mean, because the uranium is encased in cladding. You're not going to be touching it. Uranium by itself is only really an internal hazard. It's the fission products after the fuel has been used that are hazardous and what's known as high-level waste. But brand new fuel that's never been fissioned before, you can touch it without much PPE. I've touched it before wearing gloves, and the gloves is mainly to protect the fuel more than for protecting you at that point.
But they could just store the actual rods out in the open like that?
Yeah, you don't need any special shielding for natural uranium. This is concentrated 235, so it's not natural in the sense that it's pulled right out of the ground, but this hasn't started fissioning, which means almost all the radiation it produces is in the form of alpha particles, which will be stopped by your skin. You'd have to breathe this uranium in or swallow it for it to cause you cancer.
Just don't eat the uranium. So you keep it in a secret vault to protect people from eating the uranium. That's awesome.
And at that point, you've got other issues because it's a heavy toxic metal. It's pretty benign in this form.
Yeah, if you were to eat uranium, the amount of damage that it does to you from the radiation versus the chemical toxicity is about even. There's been a few studies done on this. Some kind of lean towards one versus the other, but it kind of just depends how sensitive you are. Just don't eat uranium.
The reason you have to be so much more careful once we pull it out of the reactor is because of those daughter products. When you take that big atom and split it in half, its instability will cause it to release radiation as it breaks down. That's the more dangerous form of radiation we have to be careful about.
Andrew, have you...
So it's not natural in the sense that it's pulled right out of the ground, but this hasn't started fissioning. That big atom and split it in half, its instability will cause it to release radiation as it breaks down. That's the more dangerous form of radiation we have to be careful about.
Andrew, have you memorized this, or are you just shooting from the hip right now?
A bit of both. It's not my exact tour schedule, but
you actually know this stuff.
He just knows his stuff.
Yeah.
And you love it.
Great.
Oh, of course.
Okay, great. That's awesome. All right. Okay.
I mean, this facility really is the perfect mixture of engineering and history for me. My two biggest passions, so I love this place.
He talks like a historian too, which is great. That's such a good combination. My best subject in high school was actually history, not math or science. Not that I did bad in math and science, but my best subject was history, which was interesting.
It's awesome, dude.
Thanks so much for the recommendation on this video. I really appreciate it. And thanks so much for watching. I'll see you next time.